I'm glad to be here and excited to talk to you a little bit about some of the research I do on understanding images of black holes, particularly in polarization. Hopefully I can convince you over the course of this talk that polarization near the event horizon is both really interesting and really important, and can tell us a lot about what's going on in this really interesting environment. So yes, just as okay. Yeah, just as a little motivation, I think we all know that basically every galaxy in the universe has a supermassive black hole at its heart, and a good number of these black holes launch these spectacular extragalactic jets to huge distances, to scales much larger than their host galaxies, to tens or even hundreds of kiloparsecs. Here's a beautiful gallery of many of these extragalactic jets throughout the universe in radial light. We've known about these jets for about 100 years, and the one that is most studied in the universe is the jet from M87, which was first discovered more than 100 years ago. And you can see this beautiful optical image from the Hubble Space Telescope, the jet emerging from the center of the giant elliptical galaxy. In radio light, we see these beautiful lobes that of material and energy that is being expelled from very close to the center of the galaxy all the way out to these jets, depositing material into the intergalactic medium. And then in the with very long baseline interferometry over the last sort of 50 years, we've been able to zoom in with higher and higher resolution, closer and closer to the launch point of this jet, to track material as it emerges, not just from kiloparsec scales, but down to the scale of much less than a parsec. And when I started in graduate school, this was the sort of highest resolution image of the M87 jet that we have. And the question was sort of, what if we go even further and go to scales about around the event horizon of this black hole that we think launches this jet? What would this extragalactic jet launching look like on scales of the event horizon of the central supermassive black hole? And so, starting years before I started in the field in graduate school, people had the same idea, and they decided to build together this event horizon telescope by linking together radio telescopes operating at millimeter wavelengths throughout the world using very long baseline interferometry. So operating at the highest frequency we've ever performed very long baseline interferometry, we're able to effectively synthesize a telescope the size of the Earth, and just using the resolution equation, resolution is lambda over d, 1.3 millimeter wavelength over the diameter of the Earth, we can get to the 20 microarcsecond scales that are needed to just barely resolve the event horizon of the supermassive black hole. And at the end of my graduate school, we were able to actually do that and actually start to probe the structure around the supermassive black hole. And we've also added information of polarization, which is here represented by these wisps of sort of streaks along the southern rim of this black hole shadow. And for the last 5 years as I've been a postdoc, my sort of driving interest has been, how do we connect these two scales? Or basically, how do we use this image to tell us things about how jets on this scale and then on larger scales out to the scales of the galaxy are launched and powered? So we know around the supermassive black hole at the heart of M87, first of all, we know there's a supermassive black hole with a mass of around 6 billion solar masses. The EHT was able to sort of resolve the uncertainty there about how massive this black hole is by comparing directly to the horizon scale structure in images. We know that it's surrounded by plasma, which is extremely hot, exceeding 10 to the 10 Kelvin in this sub-Eddington accretion flow, which is extremely dilute, and in particular is not in equilibrium, and so has electrons and ions which have different temperatures. We know it launches this powerful relative big jet at large scales. And we're able to take images of it on all these scales from this large scale jet down to the central supermassive black hole by looking at the synchrotron radiation produced by electrons gyrating around magnetic field lines. But we still don't know, I would say, most things about this source. And questions I think about, particular, well, sort of fall in different categories. Today, I'm not going to talk about some of the work I've done on understanding how we can use these black holes to do tests of gravity, or how we sort of try to understand what's going on in the plasma around the black hole to understand what accelerates electrons to really high energies and might power flares. But I'm going to talk mostly about how we can use these images to try to understand better how jets are launched. And in particular, if we can try to determine with future images from the Event Horizon Telescope, if jets are indeed launched by extracting the spin energy of the black hole, which I think has been the sort of leading contender for the mechanism for powering these jets, the so-called Blandford-Znajek process, for over 50 years, but it's never empirically been tested on these scales. So as I mentioned at the top, I'm using polarization to try to answer these questions. And so why is polarization so useful? Polarization is useful because we're looking at synchrotron radiation, which is emitted by electrons gyrating directly around the magnetic field line, and you can work out that the angle of the polarization, the linear polarization, makes on the sky is actually perpendicular to the direction of the magnetic field projected at the source. So you can just sort of see that in this little animation. And here in these images, the ticks here represent the direction of linear polarization, and the color represents something about how polarized it is. So just a simple model, you can say, okay, we know that we're seeing synchrotron radiation. We know that it's emitted by electrons that are polarized perpendicular to the magnetic field. So we can just rotate all the polarization vectors in our image to get sort of a maximum magnetic field in the around the black hole. It should be super useful because we know this magnetic field is what launches the jet, and we think maybe it's launching it by extracting the spin energy of the black hole. Unfortunately, things are a little more complicated when it comes to these systems, to these near horizon black holes, because we have the effect of polarized transport. So we have the light rays that are bending around the supermassive black hole, bent by the strong gravity in this region, and also are traveling through are traveling through plasma, which changes the direction of polarization. So this polarization transport is both sensitive to the space-time around the supermassive black hole and the plasma that's still in it. But that in itself also could potentially be useful because it allows us to learn more about not just the magnetic field, but also the space-time and the plasma. If we can sort of build a model for all these effects and try to disentangle everything. So in whole, it's very complicated, but polarization images are highly constraining of near horizon astrophysics, and I hope I'll be able to show you that they're actually, of course, the most constraining information we have about what the environment around these supermassive black holes is like. Yeah, so this is an outline of this talk. I'm going to talk a little bit at the beginning about how we make polarized images of the black hole. It's a very quick review of how we produce these images from data from the Event Horizon Telescope. Then I'll talk about how we have compared these images to simulations and what we've learned from that process. Then I'll sort of step back from simulations and talk about in a more simple model what we can sort of learn from these polarized images about jet launching, how we can sort of condense some of these concise simulations down to a more physical picture. And hopefully if I have time at the end, I'll talk a little bit about what we might hope to do in future observations. But yeah, I'm happy to not get there. Please ask questions as I go along. If anything is confusing, I'll throw it out at the animation section as well. Yeah. Okay. So the first bit, I'm going to talk about how we have obtained the first images of black hole and polarized light. This is work that I led as part of the PhD collaboration back in 2021. It has been expanded on in the last few years, especially with the paper that just came out last month. So the EHT is an array of 9 telescopes at 7 distinct geographic sites around the Earth. And as I said at the beginning, by connecting these telescopes, we're effectively able to synthesize the telescope with the size and resolution of the Earth. But the EHT is also a collection of people that represent more than 300 members from basically all 5 continents, 60 institutes, and 20 countries around the world. This is just a small sample of us at one of our recent meetings. But this work in particular at the beginning of this talk was really a collaborative effort that is led by this entire global collaboration. So the EHT works by this technique called very long baseline interferometry. Basically, we have 2 telescopes that are very distantly separated on the Earth, and by correlating the electromagnetic field the electric field that we receive at these 2 telescopes, we're able to learn something about the structure of the image on extremely small scales that both of these telescopes are observing at the time. And in particular, each baseline or separation between 2 telescopes corresponds to one Fourier component of the image. So basically one measurement in this what we call UV plane, where U corresponds to east-west spatial frequencies and V corresponds to north-south spatial frequencies. So basically each separation between telescopes gives us one plane wave in a Fourier decomposition of the image. And of course, that's not very much information if we want to try to learn something about the structure of the images. Fortunately, we have multiple telescopes, so we have multiple different baselines connecting them. We're also the rotation of the Earth. So the EHT, like all interferometers, operates with this Earth aperture synthesis model, whereby the fact that the Earth is rotating underneath our source allows us to sort of build in more points in this plane of complex frequencies, just because the separation between telescopes is changing as viewed by the source. So I'll just click on that video again. Yeah. Basically, as the Earth rotates, these baselines change as seen by the source that we're observing. We're able to sort of fill in more data points. But at the end of the day, we have still a very sparse number of data points to work with. And so it's not just like we're taking a picture of the source directly, of the black hole directly. We have to sort of invert this very sparse collection of data into what we think is sort of the best guess image of the supermassive black hole that we're observing. So this sparsity alone would be itself a challenge, but we have additional challenges when it comes to operating the EHT at the extremely high radio frequencies that we're observing at. So these 1.3 millimeter wavelengths or 230 megahertz is the highest anyone has ever pushed this technique. Well, except EHT itself is now going to even higher, so I'll talk about that at the end. And so we have additional challenges which are caused by the fact that we don't just have a clean recording of our sort of two polarizations as they come from the sky onto the ground. We have sort of these phase offsets from atmospheric turbulence, which cause us to lose a lot of information which would otherwise be extremely valuable. So basically, as the atmosphere is turbulent between different sites, it introduces delays in the signal that propagate from the source to us. And without knowing those delays, we lose a lot of information, particularly in the phase of the Fourier transform. We have amplitude offsets from sort of miscalibration or not perfect calibration of our telescopes. And for polarization, we also have leakage from sort of mixing polarized signals in the signal chain of our electronics, which all of these introduce additional sort of systematic uncertainties which we have to account for in trying to reconstruct an image from the data that we measure. So basically, solving for the image is not a trivial process, and it's something that the EHT has devoted a lot of resources to trying to develop new and better ways to do this more effectively and with less and less bias. And we can sort of abstract this all into sort of a black box called the reconstruction algorithm, where we take our measurements and try to reproduce the best image of our sources we possibly can. And like I said, the EHT has developed a bunch of different ways of doing this, which I won't dive into in this talk. I'm happy to talk about more questions. Basically, they fall into different camps, with some of them being based on sort of the traditional methods from radio interferometry that have gone back sort of 50 years, or from the clean algorithm. Some of these fall into sort of regularized maximum likelihood approach, which I've spent a lot of time developing. And more recently, we've had sort of full ovation and CNC posterior exploration of trying to solve for sort of the uncertainties of individual image pixels. But yeah, part of my work on this, starting with my PhD and going forward, I worked on the building the EHT imaging software library, which I just want to advertise here because it's sort of a toolkit that we put together for analyzing EHT data, but it has a lot of applications for radio astronomy beyond just reconstructing images from the EHT. It's usable on things like all my image here, multiple frequency data. And so yeah, people work with radio data and want to try something new. I'm happy to chat about that later. But like I said, I think one of the advantages of EHT is that we don't only have one algorithm for turning our image into data. We have many, and we sort of focus on trying to understand what the common features that each algorithm is picking up are. And so we can sort of narrow in on what the most trusted regions of our image are, the most trusted features are, rather than where if we only had one algorithm, we might not know what features of an image are being driven by particular priors or choices that that algorithm is making, or particular uncertainties or methodological choices that we don't have control over. And so by doing these comprehensive comparisons between many different algorithms with many different underlying assumptions or priors, we're able to really hone in on what we think the robust features are. And we've done this with sort of all of our data sets. This is just an example from our first polarized images of the black hole in M87 from 2017. And you can see from 5 different methods, they all show very consistent source structure with a few differences, but overall they show a very similar intensity structure with a constant ring diameter of about 40 microarc seconds, which is exactly what we expect for providing scale structure around the 6 million mass black hole in M87. And they show polarization structure, which is sort of predominantly helical. It has a sort of characteristic right-handed helix pattern. Consider the axis into the board. And it has an overall sort of weak polarization fraction of about 10%, which is at its base much lower than we might expect from synchrotron radiation, which tends to produce much higher polarization just directly. And we've recently, like I said, last month, updated this result with 3 years of EHT images covering 2017, 18, and 2021. So this is 4,000 gravitational timescales in M87. And we see that the image quality is improving over these 3 years as we sort of added new telescopes and improved the electronics and the ones that we already have. But all of them show very consistent structure in the underlying total intensity image in grayscale here. But interestingly, the polarization structure is actually shifting and changing over these 3 years. It seems to be the polarization fraction seems to be lower in 2018, 2021 than it was in 2017. And sort of the direction of this polarization helix is shifting a little bit. And this, as you'll see in the second part of the talk, is posing a big challenge to some of our theoretical models that I've spent a lot of time thinking about in the last few years. That's too bad, but it's also, I think, a very interesting and exciting opportunity to try to understand what's driving this polarization variability, which ultimately is tied, I think, to changes in the structure of the magnetic field and plasma around supermassive black hole on these event horizon scales. Okay, that's just the lightning review of how we make images with the EHD and how we make polarized images. I don't know if there are any questions at this point. Great. If not, I will jump into what we've learned from comparing these images to simulations. So our best tools, sort of theoretically, for understanding and interpreting black hole images are these general relativistic magnetohydrodynamic simulations, which I know many people in this room have worked on themselves. So the GRMHT simulations are these supercomputer simulations which solve the coupled equations of plasma dynamics and a magnetic field around the supermassive black hole in the Kerr space-time. Or they can, the principle work with many metrics. So we usually use the Kerr metric for a black hole. And they're really well adapted to these, to simulating these low luminosity accretion systems like you think that we are seeing in NME7. Of course, that gives us, if we run one of these simulations for a long time, and we can get pictures like, or movies like this, where we see the evolution of the gas and magnetic field on the left. But in order to turn that into a synthetic observation or something that the PhD might see, we actually have to run this radiative transfer process where we take all the data, all the complex 3D turbulent data that simulation is producing, and we run it through one of these PR radiative transfer curves. What these do is they track light rays as they're bent around the supermassive black hole, and they track the emission of synchrotron radiation as it propagates along these curved rays and produces these highly lensed images of supermassive black holes like this in full polarization. So we can't really see it here, but there are little ticks here corresponding to the polarization that are against the ground. And these still consistently include for all sorts of complicated plasma effects like the internal Faraday rotation of the polarized light along these rays, as well as the light bending from general relativity. Question? Yeah.
Just a curiosity, actually, the simulations that you were showing, are those 2D simulations or slice casts of 3D simulations?
I'm not sure about this exact one. This is just a movie I've used for a long time. But in general, they're 3D simulations. Yeah.
Okay. Okay.
Yeah.
So they're
when these images are 3D simulations, yeah. And all the images we compare to PhD results.
Okay.
And that's actually really important because if you look at 2D simulations, they have lots of weird asymmetric structures.
I was going to ask that, in fact,
Yeah.
because I was wondering.
Yeah.
Taking it out.
Yeah, so what we do in where I can get rid of this. Yeah, what we do in the EHD is we build these large libraries of geometry simulations that cover a large range of parameter space and things like the black hole spin and the structure of the magnetic field. And we produce images from them employing also a large range of different electron heating models. This is extremely important because you're in this true temperature plasma limit where, because the plasma is so dilute around these black holes, the ions and electrons are not in equilibrium, and the simulation actually doesn't tell us anything about the electron temperature itself. So we have to make additional assumptions about how the electrons are related to ions. This introduces another parameter that we explore in these huge libraries of simulations. And here on the left, you can see just a sample of a few simulations in this library, which are also dynamic and evolving in time and turbulent. And on the right is what these images look like when we blur them to the resolution that EHD actually observes at. So we think, underlying what we actually see with EHD, which is just what we can start to pick out with the telescope the size of the Earth, that there's actually all this turbulent structure and spin photon ring which we can't quite resolve, but we see something on these things. And one of the most important parameters in this library that we're really interested in trying to understand if we can distinguish between when we started first looking at comparing images to simulation is this dichotomy in these simulations that emerges between sort of the strong and weak magnetic field limits. So these are two accretion states that depend on basically how much magnetic flux you pile up on the horizon. Ultimately, in the simulations, it comes down to how you initialize the initial magnetic field. But you see that the magnetic fields either sort of go to one of these two states, depending on these initial conditions. The sort of original paradigm that people had for many years was that magnetic fields should be weak and turbulent, and sort of dragged around with the gas. You can see here, like there's these loops of field that are dragged around and carried around by the motion of the infalling plasma. This is the so-called standard and normal evolution paradigm. But then more recently, over the years, people developed this magnetically arrested disk paradigm, where instead, by starting with a more coherent magnetic field on large scale, you can actually build up fields onto the black hole that starts to push back against the infalling matter air, stopping it from accreting onto the black hole. So you get this so-called magnetically arrested disk. And in this scenario, the fields are coherent and ordered and strong. And sort of understanding which of these is actually describing the environment around the supermassive black hole is important because according to the sort of Blandford-Znajek jet launching paradigm, if you have a stronger magnetic field, you can more easily launch powerful jets because the power of the jet is related to the magnetic flux in the black hole squared times the spin squared. And so we know that M87 launches a jet. It seems natural that maybe a magnetically arrested disk might be a good candidate for launching this jet because it sort of represents the most field you can pile up onto the black hole in these simulations. But it's not something we knew for sure, and we had to go in directly into the images to compare the data to see if this scenario versus the sort of original standard normal scenario is more likely. So the first thing we learned when we just looked at EHT images in total intensity, so before we added any polarization, is that the EHT images were actually incredibly consistent just on their face with this GRMHT picture. So GRMHT simulations automatically from sort of the plasma temperatures that you arrive at and the sort of gravitational lensing and redshifting effect as you go closer and closer to the black hole, produce images where you see sort of a ring-like shape around the right size for M87. And they also feature this characteristic north-south asymmetry, which is caused by the Doppler boosting of plasma as it rotates in clockwise in the sky, in this case, with the angular momentum into the plane of the sky. So this is, I think, was both reassuring that we're broadly getting the features of this near horizon accretion correct, but also posed a lot of challenges because it turned out that most of our models in this large library of simulations could actually be made to fit the images that we observed if we tweak some of the free parameters that we have, things like the total flux density, things like the overall mass within a certain uncertainty, or the position angle rotating with it on the plane of the sky. We learned that the black hole spin faces away from us just from this overall asymmetry. Again, you need the material rotating clockwise in order by the right-hand rule to have things coming towards you on the bottom side. But overall, we weren't able to really constrain this space of different simulations, and particularly we weren't able to distinguish between the different types of magnetic field configuration by just looking at total intensity images overall. They all sort of produce ring-like images around the same size. And you can see that here, these two on the left are stains or sort of weak field simulations, and this one on the right is the magnetic field. We knew this from looking at the simulation that by going to polarization, the situation changes completely. So here's a sort of 4 different polarized simulations. And you can see that the underlying total intensity image in grayscale here, between all of them looks pretty similar. It's all around the same size. But the polarization on top, represented by these ticks and the colors and orientations, is completely different. You can have simulation images with strong or weak polarization and patterns which are radial, toroidal, or helical. And so immediately just looking at the images, we know there's a lot more information in polarization, which we can constrain the simulations by comparing them to data. And we did that by sort of extracting from all of our simulations from this library a few key parameters, which we then compared to the data. So these are things like the unresolved and resolved polarization fraction from the image, basically how much polarization there is if we look at the black hole both with 0 resolution, just the point source, or if we start to look at it with the resolution of the EHT, just picking out things on the scale of the EHT beam. And in particular, what turned out to be sort of the most constraining feature of these images is this so-called beta 2 metric, which you can think about as just the Fourier transform of the polarization around the ring. So basically, you take the polarization field and you do a Fourier transform, decomposing it into different modes. And if you look at the second mode here, you get this coefficient called beta 2. And another way to think about beta 2 is that it has a really nice analogy with E and D modes in cosmology. And so beta 2's of different values, whether they're complex or real, tell you things about whether you're in a radial polarization state or beta 2 of 1 or a beta 2 phase angle or 0. If you have a toroidal or ring-like polarization pattern, you have negative beta 2, or if you have helices of the different signs, either right or left-handed, by being imaginary or a mixture between the two. And because we, at least in the initial 2017 images, had a very clear sign of this polarization helix being right-handed, corresponding more to this image here on the right. It turned out this was actually the most constraining feature we had in terms of connecting our results to our images to data. So we scored the simulations against the polarized images in many different ways, sort of the simplest possible way, which still gives the same results and effectively is more complicated way, is just looking at the total number of passing images from different simulations. By passing, we mean like how many images within a simulation metrics which fall into the measured range. And you can see immediately from just the total number of passing simulations that it's mostly the magnetically arrested cases that pass. Very few of these standard normal evolution simulations produce the right a significant number of images which pass all of our tests. By honing in on these magnetically arrested cases, we're able to actually constrain M87's accretion rate by 2 orders of magnitude. So we only have 1 order of increment certainty for the accretion right now versus 3 previously. And the near horizon magnetic field and temperature to be on this higher end of tens of Gausses instead of much less. Again, sort of this preference for magnetically arrested accretion, which has emerged from comparing our simulated data, has lots of implications for understanding how jets are launched. Because these stronger magnetic fields more easily launch jets at sort of all values for black hole spin, it means that whereas in a sort of standard normal evolution case with weak magnetic fields, you might need an extremely high spinning black hole to produce anything like the jet power we see from M87. And that for a magnetically arrested disk, you can have a much more moderate value of spin and still get the same jet power. Of course, this is all what I said on the slide and on the previous slides is all from the initial results, the sort of new results which we just released last month. Challenge this picture a little bit because we're seeing shifts in the polarization over time. I'll talk about that a little bit more in a sec. But we haven't done the full polarization scoring analysis yet on this level for those results, so that should hopefully be coming pretty soon. That might save you.
The fact that you observe jets at much larger scale, does that pose any constraints on these models?
I think if you have to understand something about like what the field strength is at the horizon. So if you were able to back up from the model of jet on larger scales, what the horizon scale field strength is and what the horizon scale density is, then that could put another challenge. Yeah.
So you still can.
Yeah. Yeah.
Question, when we think about the presence of jets through cosmological time, of course, we can't resolve the black hole strength gas. So we know that rate is much higher. So I'm just wondering if you can say a few words about how these observations of local black holes can inform about Higgs.
Yeah, I think that's a very, so there's been a lot of work recently on trying to understand what sort of this magnetically arrested state, what its implications might be for the spin evolution of black holes over cosmic time, because it actually turns out that when black holes are launching jets in this mad state, they're actually spinning down. And so that is an important ingredient, which you might have to plug into sort of models that predict the black hole might spin up from mergers or from persistent accretion within disk, for example. Yeah, I think it just, and then another thing is that, yeah, how the mad state works in sort of the much higher accretion rate limit is another question that I think has begun to be explored, but not fully explored yet. So I think if indeed this mad state is sort of more persistent over a cosmic time, or if it's more intermittent, it's a really interesting question. Yeah, the last thing I'll say here is that we've also done a similar analysis for Sagittarius star, the black hole in our galactic center. We made images of polarization which actually look a lot like the image of 97, the polarization with similar polarization fraction, so a little bit higher, sort of 25% instead of the 10 or less than we saw in 97. A similar sense of this helix of polarization vectors around the image, which is actually consistent with the clockwise rotation that's measured from near-Earth flares. As I'll say in a little bit, we can connect sort of this sense of the polarization spiral to what we expect the direction the magnetic field line should be rotating in. And if we assume that connection, then we would assume that clockwise rotation is what we expect for any tether. I mean, for that time. Also in the sort of simulation analysis for Sagittarius star also preferred than the arrested simulations, but notably, we don't see a jet in Sagittarius star, at least on these horizon scales. And so I think it raises an obvious question that if we do prefer magnetically arrested simulations for Sagittarius star, if we do think that the black hole around Sagittarius star is magnetically arrested, is it consistent that we don't see a jet? Like, do our best models for producing jet emission actually, do they agree that we should be producing emission that is too dim for us? So I think that's something that a lot of people are working on. Yeah, any questions on that before I jump into the next?
Yeah. Do you know that the base models in the numerical simulations span the full space of possibility?
Well, they probably don't.
So for instance, they're all rotationally supported with large systems.
Yes. So we know for sure that these models do not span the full range. So for example, we're going to start with almost all of them with toruses, which are either aligned or anti-aligned with the spin of the black hole. In general, the initial matter shouldn't have to be aligned or anti-aligned, or we should have tilted disks. Or Sean has worked a lot on sort of more consistent feeding of Sagittarius star black hole from large scales, for example. So the initial conditions is something we know that we're not fully exploring. The sort of like temperature model, which we assume is also sort of based on some of our best guesses of what things look like in collisionless plasmas, but it doesn't. We don't think it spans the entire space. So yeah, I think there's a lot that we're going to be done in pushing this parameter space to be more complete, but we're already pretty challenged by what we have. So. Okay. Yeah. So in this next section, I'm just going to step back a little bit and talk about what we can learn about jet launching from looking at the polarized images 97. What is, if we just try to step back and connect the simulation analysis that we just did to a more simple analytic model, is it consistent with images of jet launching? And so backing up, we know that this is important because M87 sits at the center of this extragalactic jet, which we can observe at all scales and at all frequencies. This is just a nice collection of images that were produced simultaneously with the PhD campaign in 2017 of the jet and the central black hole. And in GRMHT simulations, we know that one of their great sort of advantages or triumphs is that they self-consistently produce jets launched by black hole spin in the Blandford-Znajek. So simulations naturally produce jets which are sort of the observed power from M87, the observed opening angle and core shift. And they have a lot of characteristics which look a lot like the images of jets which we observed closer to the black hole. They also struggle in some ways. For example, until recently, it was sort of unclear how to get the observed limb brightening of these jets. But still, that's sort of an indirect connection. And it would be really nice to have sort of physically meaningful observation of energy flow or connection between the polarization which we observe and the direction that energy is flowing in simulation. And so to do that, we turn to trying to understand what is going on with this beta 2 metric or this polarization spiral. Again, this polarization spiral second Fourier mode, we turned out to be the most constraining feature of near horizon black hole images. But when we first did this analysis, comparing the measured value of beta 2 that we observed, which again is sort of more of this right-handed polarization spiral state I'm seeing here, we didn't know exactly why that might have to be the case. And so the question became, can we actually try to interpret this polarization spiral physically? And so to do that, we turned to like a very simple cartoon model where we abstracted away a bunch of all of the sort of complicated physics of Faraday rotation, of relativistic parallel transport, or special relativistic aberration that actually does modify the polarization vectors that we observe. And we just tried to look at a model of based on force-free magnetic fields observed based on observer in the equatorial plane. And here's the coordinate axis points into the plane of the sky. And again, so here we're seeing polarization vectors which have this right-handed spiral, and in this case we can just rotate the polarization vectors by 90 degrees to get an inference of the magnetic field geometry, and that would tell us that a magnetic field has sort of a left-handed spiral or a sort of toroidal component related to its radial component, which is less than zero. A ratio of the phi of the r component, which is less than zero. And this sort of is an extremely naive assumption to make, because again, we're mixing a lot of the very important physics that we know goes into producing images. But it turned out that this ratio of field components actually is extremely interesting, because if we assume that the magnetic fields are rotating clockwise, which is something we had already learned about the M87 black hole just from looking at the overall asymmetry of the image. We assume that the magnetic field is rotating with the plasma clockwise. Actually, if you just look at the very simple equation for the radial pointing flux, so the radial outward flux of energy in this setup, and then actually it's directly related to the ratio of the radial and phi component of the magnetic field, such that it's positive if these have a negative ratio. And so this is sort of an indication that actually maybe by measuring this positive right-handed spiral of polarization vectors, we actually might be learning something about the direction of energy flow, and that it's consistent, at least in a simple model, with the energy be flowing outward along the scale that we're observing. Of course, that raises the question immediately, like, is this simple model something that actually holds up in more complicated full simulations or more complicated models? And so we turned then to starting to look at like this whole library of simulations and trying to understand, can we explain the dependence of this beta 2 phase that we measure in the simulations with this simple model. And it turned out simulations actually agreed extremely well with this model, and it's such that if we orient the black hole in the direction that we think that the black hole is oriented, the spin vector pointed away from the Earth, basically all the simulations have a negative value of this phase of the complex beta 2 number, which is consistent with this right-handed spiral of polarization vectors. And consistent again with the fact that we know there's energy outflowing in the simulation. So it turns out that this beta 2 is telling us something, that basically there is energy outflow in the simulation, and we're measuring it on the scales that we are observing in the EHT image of M87. Also, this beta 2 value has a strong dependence on the spin of the black hole. You can see that here, where basically beta 2 goes from this minus 180 corresponding to more toroidal or less helical fields to closer to zero as we increase the black hole spin, corresponding to a much more radial value of the polarization pattern. And this is exactly what we see in very simple models with just the Blandford-Znajek model. This is coming directly from the fact that polarized images are tracing the underlying magnetic field, which are spin dependent. So the black hole spin is winding up fields which are initially radial, and then it's winding them up faster if the spin of the black hole is larger. So if you increase the spin from 0 to its maximum value of 1, you get fields which are much more wound up or have a much larger phi component. And that basically increases what we call the field pitch angle. And this increased field winding is increasing the power that's outflowing in the jet, but it's also changing the pattern of polarization which we observe. And we're able to, by connecting the simple analytic model to these simulations, we're actually able to sort of explain for the first time exactly how these polarization patterns are changing with black hole spin. You can see this from the low spin, you have a much weaker, more toroidal pattern, and in the high spin case, you have a much more radial pattern that's being driven by the fact that the underlying fields are being wound up much faster in that case. And that's captured in this beta 2 statistic, where we see a strong evolution with spin and sort of just the overall distributions of beta 2 over the entire library of simulations that we explored. And if you just sort of naively compare this one value, again, neglecting a lot of very important stuff, which we need to worry about in connecting simulations to the data we measure, you just compare this one value to the observation we make in M87, it would actually sort of indicate that we're looking at either sort of a more weakly spinning black hole or potentially a retrograde model. The retrograde model winds up less quickly with spin. This is another area where, again, if I given this talk like a month ago, it would have been easier to claim victory because we've seen agreement sort of both with the 2018 results and the 2017 results. But this new result from 2017 has actually rotated the observed image sort of out of this band, and isn't as consistent with any of our simulations. And so I think it's gonna be a challenge for us in the coming, few months to try to explain this. It could be due to some change in the Faraday rotation of, the polarization as it travels through the plasma, all the plasma between us and source. It could be that we actually are some sort of this more retrograde case. You can see it's actually sort of consistent with a sort of mildly spinning retrograde case. Or it could be that we are seeing something which isn't actually captured in any of our simulations, and maybe it's an initial condition that we're not exploring well at all. But yeah, just in general, this overall variability is extremely interesting. I think it poses a big challenge to this model, but also to sort of our general understanding of what's going on.
Is there any chance that the shift is not real?
I think it's real in the sense that it's real on the image plane. We did a lot of tests in the same way that we did for 2017 with the 2021 data, to validate that the images were robust. But yeah, it could be something along the line of sight. It could be along the lines of anything that's from, close to us to further out things than jet of 7. But yeah, I'm pretty sure it's real. And of course, we've taken data in years since 2021 as well, so we will have images from that as well, so we can see if it's sort of an outlier or if it represents really something that is persistent. Okay, let's get that.
Do events like that happen in your simulation? So you have,
Yeah, so that's captured a little bit in these histograms, right? Where, yeah, there are, especially for the retrograde model, being material sort of at the interface between the retrograde disk at large scales and sort of where the plasma is dragged to co-rotate with the black hole. You're seeing sort of exactly that interface region in the EHG images of retrograde models. You actually get sort of a range of this beta 2 value, which can cross through. So it actually is consistent with some of our retrograde models and moderate fit retrograde. But there are other reasons where it's that sort of challenging, like they have to be sort of jet power. They might have other features in the image. Again, we haven't done the full scoring analysis to really try to see what simulations are preferred or if any simulation parameters are preferred across all 3 years, combining all of them. But hopefully that will come pretty soon.
Quick question, in retrograde is just once you're not aligned anymore, you have 300, you have full 4 pi to choose from, not just the opposite. That seems a bit.
No, absolutely, yeah. No, that's a huge simplification that we make
Right.
in sort of just setting up these practical libraries. I think now that we have much faster code that can run libraries over a much larger range of parameters efficiently, we actually can maybe start to fill in some of these tilted disk models and start to look at what do images, not just the aligned or anti-aligned disks look like, but over the full range. But yeah, people have produced images from those parameters before, but not in the same sort of systematic way that we've done. We're not as much in interest. Okay, basically out of time. I'm just gonna say in the last part, one thing about what we hope to do next to determine the jet power source, and it's really all the main takeaway message here is that with the EHT, we've only looked at one scale. We've only looked at sort of this one donut of emission, one radius of emission, but we know that this connects to the large scale jet zooming out, and we know that it connects to the black hole itself zooming in, and sort of by improving our instruments both in dynamic range by looking at low brightness emission, we can try to connect the EHT scale that we're observing in the horizon here to the large scale jets, and by improving our resolution, by sort of increasing the distance between telescopes that we observe with, we can try to look closer to a black hole and sort of sharpen our eye here. And there's a lot of interesting things this can tell us about energy flow on different scales, but I think we are in a perfect place to do that right now with sort of 2 directions that sort of the global near horizon astrophysics community is moving forward in the next 10 years. One is sort of by expanding the EHT ground-based array on Earth. We've already done this over the last 5 years, adding a few new sites. Hopefully over the next 5 years and beyond, we'll add even more. And we'll improve the sites that we have already to move to multi-frequency observations, which will allow us to calibrate things like Faraday rotation much better. And by increasing the bandwidth of all these sites, will increase the sensitivity and allow us to really connect the emission that we're seeing on the scales of the sort of horizon scale shadow to the larger jet scales. And then I'm also part of this mission proposal called BEX, the Black Hole Explorer, which is a NASA small explorers mission proposal, which will be submitted next time that there is a small explorers opportunity. And this would basically add a site to the EHT in space, sort of emitter orbit, sort of triple the resolution of the EHT. And the goal of this proposal is to really sharpen our resolution, so that we go into like this to this and really hone in on this really strong lens gravitational feature called the photon ring. But also in the jet launching science case I'm very interested in, it has a lot of implications for trying to basically connect the near horizon polarization emission that we're observing at one scale to a range of scales and get closer and closer to the event horizon of the black hole itself to really see if we can track the origin of energy from the horizon out to larger scales. So I think these two directions which we're moving toward in the next 10 years should allow us to answer a lot of these questions that are being posed by this first generation of observations in much more detail. Hopefully hone in on understanding what the jet launch mechanism is around M87 and potentially in other sources. And yeah, I think the future of near horizon astrophysics is bright. Happy to answer any other questions we have. And yeah, thank you for your time.
Very much. We already had many excellent questions. And more.
I think you might have had a slide on this, that you didn't get to talk about, but like when the polarization vectors undergo Faraday rotation on their way to us, would that be like the same amount of rotation for all of the polarization vectors?
No, very good question. The slide I skipped, so excellent. So yeah, there's different types of Faraday rotation that we deal with. We deal with so-called internal and external Faraday rotation. So internal Faraday rotation is something that is captured in our simulations. It's basically being driven by material close to the black hole. And for those, different pixels in the image can experience quite a different amount of Faraday rotation, depending on sort of the turbulent material that they're passing through. And so this is a comparison where we have on the left a simulation with Faraday rotation in the radius transfer, and on the right simulation without. Without, you can see that the polarization vectors are very aligned, and they're very directly connected to the magnetic field underneath them. And on the left, it's scrambled, because each of these pixels is experiencing a different amount of Faraday rotation. And what that means is when we observe with EHT, basically all this small scale Faraday rotation results in both an overall shift of the direction of the sort of spiral of polarization, and also a sort of decoherent where the image is depolarized on the left. So basically all these different scrambled vectors cancel each other out, and we can actually start to get closer and closer to the low polarization fraction which we actually observe. And so we think that this small scale Faraday rotation is extremely important for producing the low fraction polarization observed. It's actually sort of a challenge for the magnetic arrested models, because you need pretty cold electrons in those models to get such high Faraday rotation, which is potentially difficult to explain. But yeah, in addition to that, there could also be a component further away from the source, the sort of bulk scale Faraday rotation, so all vectors equally. Disentangling all of this is quite complicated, and I think what we really need is multi-frequency observations, which thankfully I've already started to do, and hopefully we'll have more analysis of in the next few years.
Already now, like, does you have already speaking of some changing polarization, external Faraday rotation doesn't mean it has to be small scale? Like, small scale in the sense of, not a 100,000 RG, but, 20 or 455 RG or something? Or can it be anywhere, like, let's say the solar system?
So I think we know, because we observed changes in the Faraday rotation measured from 1908, that at least a good part of it is happening very close to the source. Yeah, we don't know yet how exactly to disentangle that and to connect those to that small scale variability. Say 50% is happening within 50 RG, and the other 50% happening on these scales. Yeah, we really need multi-scale and multi-frequency observation.
You mentioned a few times the difficulty with the electron temperature, and I saw here also as a slide on that skip. I'm sort of curious how, so obviously you say you're not equilibrated, but.
Yeah, that was perfect. Yeah, so connecting to the Faraday rotation again, so to get the amount of Faraday rotation that we observe, we need cold electrons. And so what we prefer in our models is stuff that's like ions, which are 50 to 100 times colder or hotter than the electrons. Electrons that are 50 or 100 times colder. And so some of the work that I have done has focused on doing these two temperature simulations, where instead of doing this looking at the ion and electron temperature and fixing them manually in post-processing, we try to plug in a model based on some biophysics small scale prescription and see if that can help consistently predict an electron to ion temperature ratio, which is consistent with observations. And what we found in a recent paper that I did is that at least with one electron heating model, which is driven by sort of a favored model for plasma turbulence, you actually can't get anywhere near the extreme ion to electron temperature ratios in magnetic simulations that you need to produce this depolarization. So basically, when we do these temperature simulations, many of the features are very consistent with what we observed from the single temperature simulations where we apply the electron to ion temperature ratio in post-processing. They produce very similar trends of this beta 2 with spin, for example. Again, that's being driven primarily from field. But the overall level of the polarization is closer to 20–30% than 10%. So it's inconsistent, and that's tied directly to the fact that we have much hotter electrons, and hotter electrons Faraday rotate less efficiently than colder. Chris?
Oh, you didn't mention circular polarization.
Have fun on that too. Can we reverse this? So circular polarization is a factor of 10 weaker than regular polarization, so it's like closer to like 1% to 10%. Basically, what we have been able to say in M87 is that we can detect it. We see it in our raw data products. We see an offset between the right and left correlation products. So we know that there's circular polarization there, but because again, we're not observing directly the images with PhD. We have to do this whole algorithmic inference of what the actual image structure is from the data. This weak circular polarization we observe is not yet constraining enough to actually let us map it around the image. So we know it's there. We don't know exactly where it is or what level it is. But we do know that the simulations show quite different circular polarization morphologies. So circular polarization could, if we can detect it convincingly, be another pretty strong probe of the magnetic field structure, temperature, and everything. So hopefully we'll get there as well next year.
It's just a curiosity, and thank you for the very nice job. So I was wondering, when you perform the numerical simulations and then you have to confirm them with the original data, you blur the image, right? So I was wondering, is there any criterion or relevant criterion with which you blur the image? Like, is it important really how you choose to blur the image to confirm the data with the simulation?
So far what we've done is sort of naively blur the image that we observe, the simulation image to 20 microarcseconds. We just take a 20 microarsecond Gaussian beam and say that's basically what we're observing when we do the image process. But you're right, that's not exactly what we're doing when we do circumvention data. So like the most self-consistent thing to do would be to actually run each and every geometry image through our full analysis pipeline, produce synthetic data from it and produce reconstructed images from it. That's just sort of prohibitive at this point. But yeah, there's an interesting question about like, could we do a little bit better with this kind of blurring?
Yeah, because like
blurring.
maybe more models would potentially image at that point.
Yeah, no, I think that's a really good question, especially as we are reaching this stage where fewer and fewer models are getting consistent with our data, especially as our data vary in time. Yeah, I think we started not to worry now more about these details than we did as part of the first pass. Yeah, absolutely. Right, let's thank Andrew again.